veselje mi je, da vam lahko predstavim predavateljico, ki bo nastopila na današnjem znanstvenem večeru, to je profesor dr. Nedjeljka Žagar, izredna profesorica za področje meteorologije na Univerzi v Ljubljani. Profesor Žagar ima kljub mladosti za sabo že zavidljivo raziskovalno pot. Po doktoratu na Univerzi v Stockholmu je bila na podoktorskem usposabljanju najprej na Švedskem, potem pa na Nacionalnem centru za atmosferske raziskave v Koloradu v Združenih državah. V svojih raziskavah se osredotoča predvsem na študij dinamike atmosferskih procesov in njihovega modeliranja ter numeričnega napovedovanja vremena. Na njeno prodornost in raziskovalno uspešnost pa kaže mednarodna projektna vpetost njenega dela, med drugimi na primer dobitnik tako imenovane Starting Grant Evropske komisije ter vodja večjih projektov za Evropsko vesoljsko agencijo. V nocojšnjem predavanju z rahlo provokativnim naslovom Neizogibno mimo, kratek tečaj o napakah vremenskih napovedi, nam bo najprej predstavila, kako je malo je širši javnosti znanega o napakah, ki se v vremenske napovedi lahko prikradejo, ter na primerih iz lastnih raziskav pokazala, kaj o teh napakah mogoče vedeti, torej katere stvari lahko dejansko vemo in za katere stvari vemo, da jih ne vemo. Preden prepustim besedo profesorici Nedjeljki Žagar, dovolite tudi meni eno manjšo napoved prihodnosti, in sicer današnji znanstveni večer je zadnji, ki bo na Zemonu, kljub temu, da se je cikel predavanj prav tukaj na Zemonu z lepim razgledom po Vipavski dolini in okolici pridobil ugled in redne obiskovalce. Sem prepričan, da bo tako ostalo tudi v prihodnje, saj se od naslednjega predavanja dalje seli na novo obnovljen dvorec Lantieri v Vipavi. Prosim.
Thank you so much indeed. Good evening, everybody. And at the very beginning, I would like to apologize for that we are running 5 minutes late. And the purpose of that is really, we wanted to let you know to read this provocative abstract and the provocative title, as Samo said. And the purpose and the reason why I wrote this provocative abstract is to provoke you to ask me provocative questions. And unless Professor Stanic is against that, I would like to invite you to interrupt me at any time with any provocative question. So, talking about weather is something everybody can do. And it's also very common to say, look, they failed again. But on the other hand, I know that all of you, you really trust us on average. And you know that if we tell you in a week from now there is a big chance for flooding again, you would take it seriously. And that really gives, I think, in the last 40 years, since we are doing this business of weather forecasting seriously, meteorology has really achieved great advances in the quality of weather forecasting, and there has been a great progress on many fields. But meteorology is always seen in the public through the operational weather forecasting. And much of my research is related to the operational weather forecasting. Even I never worked as a forecaster, even although I spent almost 7 years in the operational weather service. So let's then start with weather forecasting. And what I'm showing you here is the operational weather forecasts of temperature. So please look only at this red curve, which is showing weather forecast from the Office of Meteorology of the Environmental Agency of Slovenia for Ljubljana and for Vipava. Vipava is the bottom plot. So this forecast was produced yesterday afternoon at 12 o'clock. It was initial time for the forecast, and the forecast evolution of temperature in Ljubljana and Vipava. You can see time is running along the x-axis. So if we look, for example, at 6 p.m. today, that would be this point in Vipava, operational weather forecast says that the outside temperature should be 8 degrees. And in Ljubljana, it should be 2. And this is another model. This is one which is operational at Arso. And this one is the forecast of temperature in Ljubljana. And today, it should be almost 8, opposite to 2, predicted by another model. So I know that you know that this forecast is not bad, this one for Vipava. Even it feels really cold outside, which is because of Bora. But the question I would like to discuss with you is how to measure the error of this forecast. And in order to understand how large is the error, in order to seriously speak about forecast errors, we have to be aware all the time that the temperature in Vipava or the amount of precipitation in Vipava or Ljubljana is related to temperature and wind and moisture and especially moisture and winds, not really at the surface, but at very many levels above the surface. We say that the weather is taking place in the lowest 10 kilometers. So one question is, can we objectively judge how bad or how good is this forecast of 8 degrees outside? And then the other question is, okay, we know that forecast is not perfect, but if we would like it to be better, we first have to understand what makes this forecast bad or good, what makes it imperfect. So in order to say how bad it is, we have to define first. This is scientific approach. Let's define what is the error. And we know what is the error. Error is the difference between the fact and the truth. And in the case of temperature now, forecasted yesterday, the fact would be the forecasted value of temperature, and the truth would be the truth. And here comes the problem. What is the truth? And I tell you, truth is not known. So now you can ask me, how can it be? How truth is not known? We have thermometer outside. So there is no perfect observation. And truth is in the atmosphere. Truth is always somewhere in between observed value and today, when the forecasting models are really good, forecasted value. Of course, if we have a perfect observation of all quantities in every grid point, then we would know the truth. But most of our observations are very, very sparse. We most often measure quantities which are not quantities which we forecast. And so really judging the error is very, very difficult. And I will go, all my talk will be about this. So, and now, after I state that the truth is not known, so even I can compare observation with the forecasted value, and I can do it, for example, in Vipava on the meteorological station, on in Nova Gorica on meteorological station, but how about the values in between? And these measurements, as you know, the most of measurements in Slovenia are just measurements at the surface. So how about the remaining 9 kilometers which define the weather? You know, in this valley, that the beginning of Bora is, especially in the anticyclonic conditions, characterized first by a certain cloud types appearing on the mountain tops. Then you see, once the Bora starts and develops, you see the cloud cap above Nanos and other mountains. So you know these are signature of Bora. So what you measure, the error which you, in the forecasted wind speed, which you can define by the difference from the observations and the forecast in Vipava or Ajdovščina, so is certainly strongly related with the error which is happening somewhere at 1 kilometer height, 2 kilometer height, 3 kilometer height, because at these levels processes which define the strength and gustiness of Bora are happening. Bora is not taking place at the 10-meter height at which we measure speeds. Real processes which are bringing those well-known features of Bora, they are taking place higher up, and the gust is just the final result. So in order to really describe errors in the space and time, we would need perfect observations continuously everywhere, and that we don't know that. We don't know them. But even I state that, here is the plot I just published in Quarterly Journal. And in this plot, I am showing you errors in the zonal wind fields in the short-range forecast, which are produced by the best forecasting model in the Earth. That is the model of European Center for Medium-Range Weather Forecasting. And what you see here is the pressure or height, and on the x-axis is the latitude. So we are somewhere at 15 north, so that would be somewhere here. And what I'm telling you, and I will try to convince you that I have right, that on average the error of the forecast is below 1 meter per second. Of course, this does not apply to Bora, and I will explain. But the main goal of my talk is to try to give you a flavor of how we are producing, how we are estimating forecast errors in such a way that we have estimates of errors throughout the atmosphere. In this case, I have estimate of forecast errors up to 80-kilometer height for the whole globe. And why do we need these estimates? And I will illustrate the importance of these estimates for the quality of weather forecasting. So this is a closed circle. We need to understand properties of the forecast errors in order to improve those forecasts. So how then, the second question was, how are these forecast errors produced? And they are, to answer that question, we need to understand how we make forecasts. And I would say there are 3 important ingredients of a weather forecasting process. One basic ingredient is a good forecasting system, which is capable first to provide initial conditions for the forecasting, because weather is the initial value problem, and then to take these initial conditions forward in time to produce forecasts. And here is the set of equations as it was wrote by Wilhelm Bjerknes in 1904, so 108 years ago. And every master's physics student in the audience will say, oh, I know this. These are Navier-Stokes equations. I can solve it in Matematiko, for example. And there are even demos, even in MATLAB, which solve subsets of these equations. But then, how about processes? Because the main letters, the main problems with solving these equations are those which are contained in the letters Q, C, E, F, and these describe physical processes. The rest is the dynamics, advection or motions. And these physical processes, some of them are illustrated on this plot. So these processes, they take a place on all scales. From the molecular scales, we have radiation. We have short wave radiations, which is being reflected, which is being scattered. And we have interaction between the radiation and clouds, absorption of that radiation in the clouds. And then we have all processes which take place at the interface between the atmosphere and the ocean, and the atmosphere and the land. And then we have a vertical transport of the momentum, moisture, moisture and heat. And then we have a very, very important impact which orography has on the flow. And Bora is a fantastic example of that. So none of these processes is by default contained in the Navier-Stokes equations, which you learn during your undergraduate or even graduate studies. So the difficulty is really how to represent all these processes, because we have, for example, formula. We have Stefan Boltzmann formula for the which relates radiation and temperature, but how to represent interactions between the water vapor and clouds. How if this water vapor and clouds are changing all the time? And we should know at every point in the atmosphere, starting from that solar constant somewhere at the top, how that radiation will change on its way down towards the surface. And that is very, very difficult. So what we do in order to represent all those processes, we split our domain, our whole world, or just Slovenia, into the number of points. And these are our computational points. This is what we call model. So we have to describe the atmosphere as a number of layers in the vertical direction, and we try to put more layers close to the surface, because closer to the surface, processes become much more complicated. And then on every of these surfaces, we have to define a grid of points. And here you see Slovenia represented, for example, this is orography of Slovenia, and the color bar represents the height of the orography. And this is how Slovenia looks in a typical climate model. This is a resolution, which is distance between the neighboring points, which is below 200 kilometers. So really everything what happens in Slovenia in climate models is what we call subgrid scale process, which means that we cannot, most of things, and we say that Slovenia is has a very complex relief, is really at the crossing point of the Alpine climate, Mediterranean climate, and Central European climate. And then in the climate models, because of a limiting resolution, it ends up having just 2 points with different orography. One has a height of 300, other 600 meters. So there is no Vipava Valley in climate model. But then if you go to the 2-kilometer grid, and here now you can see different valleys, but this grid contains so many points that we can cover with such grid small areas, but we can't cover the whole globe. And then the problem is, once you go to such a very, very fine grid, you need to represent explicitly so many processes which really do not have formulas which describe them. So it's really a very large challenge. And then, if we want to do good forecasting, we solve those equations. We need initial conditions. And they are obtained from, of course, from observations. This is the observation count at the ECMWF, the leading center for global forecasting. And you see how the number of observations was evolving since 1996 until 2010, and the brown bars represent conventional observations. These are conventional observations, surface stations, aircraft data, and radio sounding observations. For example, here we have, in Slovenia, we have surface stations, and there is one sounding observation done around early in the morning in Ljubljani. So that gives us all information we know about the atmosphere, about Slovenia, unless we use satellites. Satellites provide what you can see from this green bar, 20 millions of observations per day. 20 millions. It's a lot of observations. So if you want to process all these observations, to make use of it to prepare weather forecast, you need really, really big computer. So in Slovenia, we don't have a computer which would be capable to process all those data. In our group, meteorology group in Ljubljana, we have a computer called Camelot, which is actually provided by the Space of Excellence Space C. And on that computer, we run forecast only around Slovenia. And this is really a research project and in collaboration with the Environmental Agency. And you can look at our website to look at some of those products. And this is the big computer, and it's really black box, as lots of us is using computer in ECMWF, which is processing all those millions of observations. So what is done? Even there are 20 millions of observations done every day. It's far from being enough. It's far from being enough to define atmosphere, to define initial state for the model in every point. So what is being done, and this is the subject of my research for almost 10 years now, we combine all those observations with everything else we know, with equations, with our understanding of physical processes, and with old forecasts and the properties of those old forecasts, with our understanding of the forecast errors. And that is what we call background information. I denote it by XB. And here are all observations. We mix that together in a smart way in the process which is called data assimilation. And then we prepare what we call analysis, which is initial condition for the forecast, and we use it to start the forecast. And then we run that forecast, and this is what I've shown on the first graph. And then forecast is run very quickly. Forecast takes much, much shorter time than preparing initial condition because of all that huge job which has to be done to take care of the observations. And then this forecast is done, but then observations are taking place continuously. Satellites are flying all the time. So we keep accumulating observations, and then after 6 hours we have collected, again, 10 million of observations. We combine them with all other information we have about the atmosphere. And that all other information is contained in that short-range forecast. This short means 3 hours, 6 hours. And again, we combine these two pieces of information. We produce new initial state and rerun. So this was forecast from yesterday for Vipava, and this is the next forecast. So actually what we are doing, we are updating our product all the time as the new information arrive. But that process in which we combine these two pieces of information, which is called data assimilation, and its product is called analysis, it has been done now in a good way for almost 40 years. And long data sets of these analyses, they have provided the basic understanding of the general circulation. They are the fundamental data set which is used to understand all motions in the atmosphere, which is used to verify climate models. And then this box, which is really taking place in order to combine observation and all other information called data assimilation, it's quite complicated. It's so complicated that for most of people, even most of meteorologists, it's a black box. And if I would like you to take only one understanding of what is data assimilation, I'm showing the tomato soup, and the point I want to make you, that even it does not exist without observations. Observations represent carrots, onions, garlic, good olive oil, but tomatoes, they come from the model. So even there is no forecast, or all forecasts are, we need observations to prepare initial conditions. But in that process of producing initial conditions, still most of information come from the previous forecast. And then after all that hard work, all forecasts are partly wrong and eventually totally wrong. After about, right now, 6-7 days, unless it's August, all forecasts fail. And we have just learned they fail because we don't have enough observations and they are not perfect. And then we are not really great in making use of these observations. And then models are not perfect. They describe most important physical processes just approximately. And then these two problems combine non-linearly. And then there is the fundamental problem, and that is that we are talking about highly non-linear system. Now, this fundamental problem, there is nothing to do about it, but about these two other problems, there is lots to be done. And really lot has been done in the past 20 years, and my research is mainly in this first problem of improving initial conditions, and also in trying to combine or to understand, combine impact of these two problems. So I will now try to explain you a little bit better why is this tomato soup so difficult to make it good? So it's all about errors. So I said, we don't know truth, but now I'm back to saying, okay, in order to prepare initial conditions good, I need to describe properties of the forecast errors, and that is described by this epsilon b. That's a difference between the forecast and the truth. And then I have to understand properties of the observation errors. That's the difference between observation at a certain point and the forecast or truth in that point. And then, of course, when I prepare initial conditions, they are not perfect. I would like to understand how bad or how good they are. That's the analysis error. And now here comes the most important part. The most important part is that the forecast error in Vipava is strongly related to forecast error in Ajdovščina and forecast error in Postojna, right? And not only at the surface. So you can be pretty sure that if the model has failed in Ljubljana, it probably has failed to some extent in Grosuplje and in Postojna. And how much it will fail at other points in relation to a failure in one point depends on what process we are describing at the moment. So at the end, we always come to understanding the nature of atmospheric processes at many scales, and not only horizontally. We have to understand three-dimensional and structure of these processes and how they evolve in time. So the forecast errors are spatially correlated, and that is described by this matrix, which is denoted by letter B, which is called background error covariance matrix. And this has been my focus for some time. So these are forecast errors, and this is the transpose, this is the vector. So when you do this product, you get the huge matrix. So if we, for example, have a model of the Earth with 25-kilometer distance between the points, you end up with, for example, 5 million points. So this vector has 5 million points. It's a column vector along 5 million points. And then you take transpose, so you have matrix 5 million times 5 million dimension. And then if you want to, you have to use it to prepare initial conditions. In that process, you have to invert that matrix. You see it's here. There is no computer which can do that. And even if you have a computer which can do that, we don't have information to describe that matrix. So what we do then, we model that matrix, and we have to use lots of assumptions, and we have tried to be smart in order to simplify that matrix. But that matrix is really very important. And why is it so important? Because if we know how the forecast errors are in Vipava are related to the forecast errors in Ajdovščina and Razdrto, then if we have observation in Vipava, but not in Razdrto and not in Ajdovščina, then we can use understanding of the forecast errors to spread the impact of observation in Vipava to points around. This is the fundamental role of this matrix, and that is shown here. So I have observation here, but no other observations. And I use my understanding of the model properties, of the properties of forecast errors, of the behavior of the atmosphere to spread observed information in the model space. And this is the very important process. So, and what even more, I use it, if that is temperature, I spread that information in all these points to the temperature field. But I know that if temperature forecast failed, then I can be pretty sure that also pressure and winds are not perfect. And how are these errors correlated? It turns out that they are correlated, at least for the short time scales, in a similar way as the basic fields. And I use this coupling, we call it balanced relationships, to spread information which is observed in this point, temperature observation, to the wind field in all other points. And what does this mean? This means if I have temperature observation in Vipava, I can use it to correct bad forecast of wind in Razdrto. And this is really smart if I can do it properly. So this is an important role of the B matrix. We call it balance. So, and this is the example. I have a temperature observation at this point, which says, oh, it is somewhat warmer than the model forecasted. And then I simply spread that information all around, because I think everywhere else, this is quite flat area. It's probably everywhere around I can do it isotropically, it's warmer. And then I say, okay, I know from the relationship between the temperature and winds, there must be wind, so I will correct also circulation. Okay, so this is the very important property of the background errors. And then one can really try to understand. One can do idealized experiments, like here I have simulated roof. This is some temperature field and wind field. And here I'm just showing you, if I assimilate only temperature or only winds, I get some information in the points where I have observations and nothing in between. And doing these curves, making them smooth, is not really just taking some spline interpolation. We have to do this interpolation by respecting physical laws. And I'm doing that here. I'm just respecting physical laws, and here I have produced, just by assimilating temperature, I have produced also wind information. And I have done here something similar by using winds, and the same here. So what I have done, I have used different methods to represent this truth, simulated truth in this case, and every of these solutions is a possible, is a legible solution of this problem. And so basically I can do lots of such different guesses, intelligent guesses of the state of the atmosphere, and they are all within a probability distribution which describes the current state of the atmosphere. So what I do then, I use all these initial states and I run the ensemble of forecasts. So the spread of this ensemble in time increases because the solutions diverge, and eventually when this spread becomes as large as the climatology, this is when forecast becomes useless. And what I hope then, that by doing these different simulations, by preparing ensemble of simulations, that truth is somewhere in the ensemble. I hope if I make large enough ensemble, that truth will be represented by one member of my ensemble. And of course, I cannot really know which member of the ensemble represents truth in advance. But posteriori, when, for example, interesting, disastrous, heavy weather happens, then I can go back and look at my ensemble members and try to find out which one represented truth best, and then try to track it back. Why that particular ensemble member was good and the others were not so close, and then I use this information to improve my forecasting system. And then in the same way, if I have ensemble of these realizations of the atmosphere in the future, I can use solutions of this ensemble on short time scales to represent errors, because differences between different ensemble members can be used as a proxies for the forecasting errors. And the speed by which these different solutions diverge is showing me how fast the errors grow. And this is, of course, dependent on the current state on the flow. And this is how I prepared my errors. I have used such a large ensemble, and then I have looked how quickly different solutions of this ensemble in different points diverge. And I use that information to represent these errors. Here you see the example. This is along 45. We are right here. We are somewhere at 16 east, right? So we are somewhere here. And this is date 1st July, 5th July, 10th July. So you can see that forecast errors, the color corresponds to the error intensity, vary all the time, because forecast errors in one day are different from forecast error other day, and then I can average that information, and eventually I end up with this plot. And this is how I estimate forecast errors. And this is what we really do today in forecasting model. We do this occasionally, and then we use stationary, almost stationary information of the forecasting error. If we are able to produce ensemble, then we update information about the magnitude of the errors, but information about the correlation of the forecasting errors, which I explained earlier, that we keep constant and that we still have to build on our understanding of the relationship between different fields, unless we use Kalman filter. And this is what has become very really not, I shouldn't say popular, I should say we are aware that we should forecast errors, but this is a very expensive problem, and currently it is still researched in many places, especially in the United States, and there are some weather services which are now implementing Kalman filter operationally, but I think that's going beyond my talk tonight. What I would like to tell you, to explain now, is that lots of my research is about understanding dynamical properties of these forecast errors, understanding how errors which develop in the tropical Pacific, for example, influence on 5-day scale forecasting errors in Europe, in Slovenia, for example, because after 5 days, all weather become global. So what is happening in the Pacific now, next week, will have some impact on average on weather in Slovenia. And I will now, I think, just quickly, because I don't have so much time left, I will tell you a few sentences about few projects which I am currently working on with several students and collaborators. And these include data assimilation, which I just spoke about, and primarily the modeling of the forecasting errors, and trying to understand how different errors in the temperature and wind field are related to each other. And of course, other important problem with the preparation of the initial state for the forecasting is how to make best use of the new observing system. So we know, obviously, that if we want better forecast, we need better initial conditions. Initial state is made of observations and the background information. So it would be most optimal to have a fantastic observing system with great precision. But still, we have to incorporate those observations in our models, in our forecasting systems. And we have to make sure that those observing systems are really giving positive impact, because models are often tuned to give best performance with a certain set of physical parameterizations, model choices, and observing systems. And sometimes it can even happen that you have a very high quality observation, but it's very difficult to ensure that that observation is giving you positive impact on your forecast quality. And this is really a big challenge. Another research area I work in is atmospheric dynamics on many scales, from really large scales, global scales, to small scales, in a complex terrain area such as Slovenia, and predictability issues. And then the field I recently moved into in relation to my participation in the Center of Excellence, Space C, and the ERC project I will mention is climate, and it's really climate dynamics and uncertainties, which are especially uncertainties related with the application of the regional climate models. So I will try to mention at least two projects, and then later on, depending on your question, I can say something more. And this project is related to the impact of the new satellite wind observations. It is funded by the European Space Agency through this program for the collaborating states of ESA, and Slovenia is now in this stage on its path to become a full member in about five-year time. And actually, I have been related to this project ever since my PhD studies. So it's almost, I started with that almost 10 years ago in Stockholm. And this is in order to understand why this project is so important, and it has been really inspiring to many people. We have to know that the majority of satellite observations are observations of temperature, or satellites mainly measure radiation, which we then derive into temperature. But observations of the winds are available from geostationary satellites. They are derived from the cloud motions. But we don't have direct observations of wind profiles from space. Still, to understand wind profile, to measure wind profiles, we use radio zones, because aircrafts which are measuring wind, we have wind measurements from the flying altitude, and then there are partial profile measurements during the landing and taking off. So this satellite, atmospheric dynamical mission Aeolus, once it is launched, it would become the first satellite which would measure vertical wind profiles. And there is something special about it. It has been planned because of the difficulties with carrying out these measurements. It's planned that this satellite would measure line of sight winds. So besides the PhD I did on the impact of this satellite and the best use of expected observation in data assimilation, I have done another studies on which this project is building up, and that was done for the EUMETSAT, European Agency for the Exploration of Meteorological Satellite. So in this project we said, if ADM is successful, how, because it is a research satellite, but if it's shown to be really giving high quality measurements which improve weather forecast, then we should launch a set of satellites, for example, 2 satellites, and the question is how to pick up best constellation of these satellites which would give us most beneficial impact on forecast, for example, over Europe or over tropics. And here you see several such examples of different constellations. Here are the 2 satellites. One is red, one is in blue color, and in different ways. Here they are just following each other. Here they have different azimuths. Here there are 2 satellites. No, here there is a shift, right? There is a 180 degrees. One is flying over Atlantic, other one over Pacific. Here they are just following each other, but measuring 90 degrees off, so that we measure vector. And here we have 2 instruments on the same satellite. And I was looking into most optimal constellation which would give better results. And why is important to really measure winds from space? It's important because from the basic dynamics, we know that measuring wind and temperature has not the same importance in our models, in our forecasts. And this goes back to late 30s and 40s of last century, and the basic arguments about the relative importance of winds and mass information on different scales. And it's not only that winds should be measured everywhere in the tropics. On mesoscale, these are scales which we really speak about in Slovenia, below 100 kilometers, and for all processes which have very large depth. Here I mean 5 to 10 kilometers. It's really more useful to measure winds than temperature information most of time. Okay, and then we have another CELS project, which is also funded by ESA, which is also coupled to this GMS program of the European Union and ESA. And it is really dealing with the issues of assimilation of moisture and wind and aerosol together in data assimilation, because when we assimilate different types of observations at the same time, these observations interact during the data assimilation. And during this interaction between winds and temperature, there is an information transfer. And the question is how to, for example, gain more high-quality information about the wind field from measuring moisture. We have lots of measurements of the moisture from satellites today. And also, if we have aerosols, can we use some aerosol types to gain, as a tracers, to gain some information about winds? And then, of course, there is a relationship between aerosols and moisture. So this is the goal of this project. And of course, this is a very difficult problem, and we shall be addressing it on a more basic level with a simplified model. And this is just example of the modeling. This is the surface ozone verification of the model, ensemble of models. Ensemble is shown by this light blue area, comparison with observations which are presented by dots for Ljubljana. This is a work being done by my colleague Nedjeljka Žagar, who will participate in this project. And then we do lots of work within the Center of Excellence Space C. I can say something more about it later if there is an interest. I would like to show this slide as my last slide. This is the project which currently occupies me most, and it's called MODES, which is not abbreviation, but it stands for Modal Analysis of Atmospheric Balance, Predictability and Climate. It's a several-year project, and in this project, I'm really doing dynamics, not data assimilation. And what we do in this project, we are analyzing atmospheric motions and predictability, and we shall also be doing some diagnostics of the global climate models, not in the XYZ space, but instead of that we shall transfer all this model information from the physical space to so-called modal space, which is a space of waves, but not any waves, special waves which are solutions, which are eigensolutions of the linearized Navier-Stokes equations. And when we linearize equations, we are able to separate motions into two kinds of motions. One which is describing balanced motions, which is a motion which dominates on scales which are larger than a couple of days and which dominates in the free atmosphere above the surface. And then inertial gravity motion. For example, Bora is an inertial gravity wave. And then in the tropics, which is tropics are driving part of our atmosphere. Tropics are also most critical part of all climate models. In the tropics, global hydrological cycle take place. And I told you earlier that if we want good forecast for longer than 5-6 days, we have to think globally. So we can't really focus only on Slovenia if we want to think about longer time scales and larger scales. So we have to think in terms of global models. Okay, and so with this, I think I will just conclude with this final remark that I think that I have illustrated that doing meteorology research today is really very, very dependent on having high-quality observations and also really big computational resources, because lots of work we are doing today is really computing. But not having big computers and having lots of money to launch expensive measurements is really not enough. We still have to understand fundamentally on the very basic level, we have to understand physical properties of the atmospheric motions. We really have to study always from the beginning then we have to be able to incorporate all these new resources which we have, to combine it with our understanding of physical laws in order to interpret and in order to make good use of these resources. And I think that we are trying, and also I know you are trying here at University of Nova Gorica within your Center for Atmospheric Research. We are trying to grow, and I think we are trying to show that even we are small groups, and that still if we have a strong international collaborations, and good working conditions, we can still contribute to meteorology, which is truly global science. And here I stop. Thank you very much. And also, I would like to thank you very much, the rector, for inviting me. It's a pleasure to give a talk in such a beautiful place.
Thank you very much. I would perhaps like to ask you 2 questions to warm you up a little bit. To my understanding, really, as you said, that the data itself is really important for weather forecasting. So the real weather forecasting that started, for example, sometime around World War II or something like that, at that time, it was a great advantage if you had meteorological stations, I don't know, in Greenland and in the north. So in this way, you could really predict what the weather will be, and this was a big advantage for military operations. At that time, of course, there was no computing, or probably, I don't know, the modeling was just done by hand. But still, there were weather forecasts. And with the advance of information technologies, we have what we have today, so we can already consider things that happen in the Pacific and how they influence things that happen here. So I wonder, what is your prediction or your vision of how much can still weather forecasting really improve in, I don't know, next decades, reflecting back on what has happened so far?
Okay, I can answer that. Thank you for asking. So it was really in the first objective forecast was done in 1950, and the way it was done was really very simple. It was done on so-called ENIAC, first computer at Princeton University, and in that project, the father of dynamical meteorology, Jules Charney, and von Neumann, who is well known to almost not only physicists, but also everybody else, because he was involved in all other projects, such as Manhattan. So they joined their efforts and used that computer to produce first objective forecast. And at that time, as you said, there were very few observations, and the maps were done, initial conditions were drawn on the maps somehow by hands and using scientific good sense. And then it was digitalized, and the first forecast was done. And actually, that was in Sweden in '54, when one of the most important dynamicists was born, Carl Gustav Rossby, after he returned from US to Sweden and established department where I studied in Stockholm. And in Sweden, they started first operational forecast. But the preparation of initial conditions, as I described it today, it started, I would say, around 1980. So, but much before that, in early 60s, it was shown by Edward Lorenz at MIT that there is a quite well-defined upper level limit for deterministic forecasting. And at that time, and by the equation he used, he showed that this limit, and this applies to synoptic scale processes. And synoptic scale processes are processes like those which have caused the terrible flooding in Slovenia 2 weeks ago, and also those heavy rains last week. So we are talking about processes which have horizontal scales about 1,000 kilometers or greater, and which are really taking place throughout the troposphere. He estimated that the limit, for theoretical limit in the most optimal case, which means with perfect initial conditions and perfect model, is below 2 weeks. And this is a consequence of the non-linearity, which means that the great sensitivity to the small changes to small perturbations in the initial condition. So today, at synoptic scales, average weather forecast from ECMWF are at about 7 to 8 days, not only over Europe, globally. So this is where we are, and we could judge that there is still a large area where we can improve our forecast. How much more improvements we can achieve, it really depends on what are the processes and scales we are talking about. On small scales, and for processes, for example, which are close to the surface, it will be very difficult to improve forecast much more because for these processes, stochastic component can often become dominant over deterministic component. So when we look at the Navier-Stokes equations, large part of it are deterministic components. Okay, we can solve advection perfectly. But those physical processes which I briefly spoke about, we just describe them approximately. There are no equations for them. Turbulence, it's the biggest problem. That is unsolved problem of the classical physics. And so for processes and times, when stochastic component becomes dominant, there is not much to do. So what is being done today is that we are really running ensemble of forecasts, also on a high resolution, and then we are trying to say, we are trying to provide information about the reliability of our products. There is a large, there is indeed a large area for improvements, and that especially in the tropics. Because in the tropics, we know that on very short scales where convection takes place, there is a large stochastic component, but on the large scales, there is really, those processes probably have much larger predictive scales. And then for global scales, we have to understand how these processes are influencing the weather in the mid-latitudes, because the dynamics which we have successfully used in 60s and 70s to understand processes in the mid-latitudes does not describe processes in the tropics. This is in mid-latitudes we know most of time processes take place on quasi-horizontal surfaces. In the tropics, everything what matters is happening in the vertical direction. It is convection. So it's really a big challenge how to understand balance in the tropics, and then how to understand the propagation of the impact of the tropics to the mid-latitudes, and what is that which is destroying our forecast after 6 days. We know about different important factors which contribute to them, but then also in different models it can be different because models are different. Even they have many things are done in the same way in the models, but then every model has own problems and issues. Yeah. So in the polar region, so if it's winter, then it's quite simple, right? It's dark. In summertime, and this is the big challenge for climate modelers, because in climate we really have to take care of the cumulative impact of deficiencies in our parametrizations. It's very difficult for the models to represent cloudiness. It's very difficult to build. For example, you can have most of time just a low cloud deck which is located not far from the surface, and which can be thick relatively, which can be just fit between two model levels. And this is a huge challenge. This is a challenge in climate models, not only in the Arctic, but also in many areas like off the Californian coast, in the areas of trade winds. It's very difficult to represent cloudiness. And the representation of cloudiness in the models have a great impact on the albedo, of course. And then this can completely change the local energy budget. So this is very difficult area to model, and this is the reason why when people compare climate models over tropics, there is a huge difference between different models. So the problem is really in the physics. No model really suffers from significant problems in doing advection. We can do that. That's something we do perfectly, almost. But how we do physics, how we really build clouds, especially if you have models, for example, in the boundary layer where these cloud decks develop, if there is a difference of 1 kilometer between different layers, and in that level you can have the cloud deck. So that's a problem, really. Yeah. And then you have floating ice and all that dynamics. Yeah. So, but I would say that the clouds and the cloud radiation feedbacks, that's the area with the largest uncertainties.
I just wanted to remark that there is, connected to this problem of cloudiness and cloud formation, there are new investigations that indicate the influence of cosmic radiation on cloud formation.
Okay.
Yeah?
Okay. Thank you.
Thank you very much.
Thank you.
Okay, some more questions? If not, I'll ask for another comment.
Okay.
Namely, not so long ago, there was a big trial in Italy regarding the prediction of future events. And of course, we all understand that predicting the future cannot be exact because of so many factors, but apparently many people still believe that the weather should be predicted right, and let's say the earthquakes should be predicted correctly and so on, which is really, from scientific point of view, really impossible. But this kind of attitude will definitely have some impact on, I don't know, on the science, in particular on the operative part of meteorology or other fields of science where actually the predicting the future is required. So do you have any feelings or any comments about that?
I think what I would like to point out that it would be optimal with every forecast to provide also uncertainty estimate. Because, for example, in meteorology, when colleagues from weather service in Ljubljani said 5 days before heavy rains, there would be rain, they were able to tell you with 100%, say 100% for sure it will rain. They can't really say, look, in Vipava it will rain 60 millimeters, in Ajdovščina 65. For such forecast, we should say, okay, we can tell you amount of precipitation with a certain safety. It can be maybe 60% probability there will be 50 liters per square meter or so, right? But for sure we can say tomorrow, I'm sure, tomorrow weather will be very, very nice weather, no rain, 100% for sure. But there is no such really high probability in seismology. And I'm not a seismologist, but even if there was a lot of small earthquakes, the probability really to say this will be followed by a big one and next month was, I don't know, really probably very, very low or below 1% or something. And you don't want to hear from me, I give you 1% chance. There may be 75 meters per second bora tomorrow. You don't want such forecast because it will scare you. So I think for such events, it's really, and for such predictions, where really there is a very, very small probability, then it becomes really critically important that civil protection agencies, that civil authorities collaborate very well with the scientists and develop ways how to really process and digest this information and present it to the public. Also, public has to be educated. If I tell you tomorrow there is 85% chance that Bora will exceed 50 meters per second, so how would you interpret this 85% probability? That also has to be learned. For example, I did my postdoc in Colorado, which is a very dry region, and in US they always give, together with the precipitation forecast, they always provide chance for precipitation. And there was a forecast one day that there was a 20% chance for rain tomorrow in Boulder, which is a very dry place. And I was a little bit even laughing, but my landlady, she said, wow, great, this means it will rain. Because in Boulder, whenever there is 20% chance, it's a high probability it will rain. So, this was just an example to illustrate that we also have to learn how to develop interpretation of these probabilities. In meteorology, it's much simpler because we do it exactly the way I showed you in this plot. We just perturb initial conditions within the range of uncertainty. And this range of uncertainty is defined by the errors in the observations and errors in everything else. And we are not absolutely sure how large of these errors, but we have pretty good idea. And then we run ensemble, and then we know that the spread of this ensemble defines uncertainty within our best abilities. So that's what we then use to say something about probability. And I can show you also another example, which is really from climate. So basically, and this is work done within our group, to a large extent by a young colleague, Luka Honzak. In Slovenia, for example, we have a very diverse air regions, and every small region, even every county, would like exact forecast, not exact information. 30 years from now, water regime will change that much, right? Everybody would like climate scenario, not only for the county, for my backyard, optimally, but that's very difficult. So what we can do in the most optimal case, we can really give you some average scenario, but this information has to be really packed together with the information of uncertainty. And for small areas, especially areas which are done within something called regional climate modeling, this becomes really very difficult. And in this example, I'm showing you comparison of precipitation over Slovenia. You see on this plot, you see observations. This is for the last 40 years. So we can compare observations, even they are not perfect, but that is as close to truth as we are able to come. So this is observed precipitation distribution. We have more stations, but here we represent Slovenia on 25-kilometer grid. And then here you have 14 different models which are really best what European regional climate modelers were able to produce a few years ago. And these are their individual results for the simulation of precipitation over Slovenia in the last 40 years. So if you look, for example, this model or this model, they are pretty bad, right? They are really not doing a good job. But average of this, and we call this model ensemble of models. And when we average their result, you see that the ensemble mean is quite good in comparison to observations. So this is an example showing that we really, for the problems in geophysical sciences and in the atmosphere, we have came pretty far in doing this. We have to do ensemble of simulations in order to account for uncertainties. And I think in seismology, this is extremely more difficult problem. So. Yeah, I agree with you that there will be much more caution among scientists, among seismologists, but on the other hand, it may also, a good thing is that it can provoke, it should trigger much more discussion, and also discussion between civil authorities, protection agencies, and scientists about how to communicate scientific results. And I think in meteorology, because of the importance of weather and then climate now, because of the trends which we are observing in the last decades, we have been learning this more because simply we had to, yeah.
Thank you. Okay. Any more questions?
Yeah, I can show this nice. This is a nice, actually, simulation done by my colleague Gregor Skok. Also, here we would like to do our own estimate of the precipitation, climatology, and scenarios over Slovenia, and this is our model, or the result of our simulation, and these are satellite observations. So, of course, I'm a more modeler. So there are problems with observations. What I would like to say, that one would like to, when verifying model results with observations, to use it to understand model deficiencies, to improve models. But also one has to be aware, always when doing comparison with observations, especially satellite observations, of the observation error. And especially many observations are also characterized by spatially correlating errors and biases. So there is this is a research area in its own, handling observations, and in order to really make best use of them. Yeah.
Okay, any more questions? If not, let's thank the speaker again. Thank you.
Thank you.